This physical motion analysis was based on a scene from the movie Titanic, which I'd like to show you now. Oopsies, that was the biology scene. Now here's the physics scene. Let's watch that again in slow motion. Notice how the man falling starts rotating as he hits the bar. Ouch, that looks like it hurt. In order to test this, we decided not to use humans. Instead, we used a simple test case in which we dropped an expo marker on a whiteboard and had it hit a magnet such that it started rotating. Here's our video of this motion. Again, let's look at it in slow motion. Once we had taken our video, we loaded it up into Video Point and started tracking points. The first point we tracked was the center of the marker, which is shown in the outlined part of the data table here. The next point we tracked was the end of the marker. This allowed us to measure the rotation of the marker as it went from rotating not at all before its collision to rotating a lot after. In order to figure out this rotation, we subtracted point 2 from point 1 to get a radius vector, which pointed from the center of marker to the end of the marker. Based on this, we were able to determine several things, including the angle that the radius vector made with the horizontal, the angular velocity that the radius vector experienced, and thus the marker experienced, and the y velocity of the marker, which was based solely on point 1, the center of mass. I'd also like to direct you to several portions of the video which are shown in pieces of this graph, or of this table. This portion of the video is the part leading up to the collision. In this portion, the y velocity steadily increases, as you can see to the right. This is caused by the only force acting on the marker at this time, gravity. Gravity causes the y velocity to steadily increase. During frames 18 and 19, the most interesting part of the video happens, and this is the part for which we drew a free body diagram. During this portion of the video, the marker experiences a force exerted by the magnet, which causes it to begin rotating and to slow down. As you can see, the y velocity steadily decreases during this time, whereas the angular velocity increases quite a bit. These are both caused by the same force that is exerted by the magnet on the marker. The force not only causes a decrease in the y velocity, but also creates a torque, which causes the great increase in angular velocity. Finally, after the marker has hit the magnet, it continues to rotate at roughly the same speed, and with an increasing y velocity, again consistent with the only force acting on it at this point, which is gravity. In order to represent this data more clearly, I'd now like to direct you to several graphs we created. These first two graphs deal with the y velocity of the marker before and after its collision. Before the collision, again, the only force acting on the marker is gravity. Thus, its motion can be approximated with a linear equation. In this case, the slope of the linear equation is negative 11.47 meters per second squared, not too far off from the accepted value for gravity of 9.8 meters per second squared. These discrepancies are likely due to measurement errors or other things like that. After, again, the y velocity is determined solely by the effects of gravity. In this case, the slope of the linear fit we applied was negative 12.4, again, close to the accepted value for gravity. However, notice the discrepancy between the end velocity of the first graph and the beginning velocity of the second graph. This again is caused by the force that is applied by the magnet between the two graphs, exactly when the marker strikes the magnet. These next two graphs show the angular velocity before and after the marker's collision. Before the collision, the angular velocity stays very near zero. This is because the marker has no spin when it is initially dropped and does not experience any torque which would cause it to start spinning. However, after the collision, the angular velocity is much lower, negative 36.6 radians per second. This great change in angular velocity is again caused by the force exerted by the magnet on the marker, which generates a torque, causing the marker to start rotating. This free body diagram shows the forces acting on the marker directly when it comes into contact with the magnet. The magnet is shown by the circle in the lower left corner of the diagram. The marker, which has a length of L, has a force exerted on it by the magnet at the left-hand side, which is shown by the letter F. In addition, it has the force of gravity, shown here by weight, or mg, acting on the center of mass of the marker. Based on this, we were able to construct our analysis explaining exactly how the change in angular velocity occurred. We begin with the impulse momentum theorem, stated as the change in momentum, or mass times the change in velocity, is equal to the force exerted on an object times the time over which that force is exerted. In this case, the force was the force exerted by the magnet, and the time, which we don't know, we'll just leave as delta t for now. This equation also has a rotational analog, which states that the change in angular momentum equal to the moment of inertia times the change in angular velocity is equal to the torque applied times the time for which that torque is applied. Because the time for which the torque is applied and the time for which the force is applied are the same, it's the time for which it's in contact with the magnet, we can let delta t represent both these quantities. We can further simplify the second equation by stating that the torque is equal to the length of the lever arm, L over 2, times the force, F, times the sine of the angle between them, which in this case is 90, leading to no coefficient necessary. Furthermore, we know that the moment of inertia for a slender rod, which the marker can be approximated as in this case, is its mass times its length squared over 12. Plugging both these values into plugging both of these equations into the second equation, we arrive at the equation that the change in angular velocity is equal to 6 times the force applied times the time for which it's applied over the mass times the length of the marker. We can simplify this even further, however, by going back to our first equation. The force times the time for which it is applied is simply equal to the mass times the change in velocity. This simplifies things quite a bit and allows us to come up with a theoretical value for the change in angular velocity equal to 6 times the change in linear velocity over the length of the marker. In this case, 68.33 radians per second. However, our actual value for change in angular velocity, derived from the graphs we created and the lines of best fit, was only 37.38 radians per second. This could have been caused by several reasons. First of all, we ignored the fact that the marker is not simply an infinitesimally small line and has in fact a width, causing perhaps a greater moment of inertia, which could lead to a smaller theoretical change in angular velocity. In addition, we neglected the possibility that the center of mass of the marker may not be in the center, or that weight may play an effect in determining what torque is applied to the marker. Finally, the video point software did not allow us to incredibly accurately detail the motion because the frames were very blurry and it was difficult to tell exactly where the center of mass was, leading to very noisy graphs and thus a lot of measurement error. All of these factors could have led to the disparity between the theoretical and actual values we determined for angular velocity. However, these results still help us show why exactly the man began to rotate when he hit the iron bar, and why this type of collision causes a change in angular velocity as well as a change in linear velocity.